Well, no, I wouldn't have got the right answer. How do I know that's stupid? You see I made that mistake because I got 4 to the power 10 because I got my numbers tangled up here and didn't write the 40 down. Straight away I've caught that because I've got a stupid answer because the probability is bigger than 1. So it's nuts. Should be that. And the point of comparison is these two guys match up here. I think that's an important thing to do. I want you to see that I can make mistakes, but I catch them because I test my understanding every which way that I can think of every single stupid time. And when you get silly answers, I can recognize it and think, oops, I've cocked up. And of course the cock up was the 10 should have been a 40. So what you do in your exam is you just airbrush this out of existence. How do I do it? How do I put Stirling's approximation in instead? Just do this. And it should be close but not identical. Give me a break. 3, 8, 9, 4. Come on. Calculate the exact probability and compare this with the value obtained using Stirling. Oh, it's here, isn't it? Yeah, it's not very good, this, is it? Let's get rid of all of this lot here. Okay. Right click, paste, and we're done. We'll just get rid of this. Pretend it never existed, which is always nice. I wish I could get rid of all my mistakes like that. That's red because it asks us to do that. This is blue because it doesn't ask us to do that. But that's got to be red because it does. So here it says the answer would be Stirling's That's all you need to say. Stirling's approximation gives an answer slightly too high. There it is. It only asks for a comparison, so really, I mean, technically you don't even need that. Really, the fact that you've got that answer there and that answer there, I'm not asking you for a point-by-point comparison. So there you go. Do you think you could do that in the exam?
Could you do this slightly darker blue?
Darker blue, yeah? Better?
Yeah.
Okay. Okay. This is Bayes' theorem here, the next question. Let me talk about Bayes' theorem. You'll remember the point of Bayes' theorem is to compare hypotheses. So you've got a prior probability for a hypothesis, H. And that's, you conventionally call that P of H. That's what I call the subjective prior. Equals belief or opinion, thoughts. And then you throw data at it, which is objective, measurable, exact, I guess. And then you get a P of H given D, which is called your posterior, equals your prior, modified by data, or modified by observations. And we've talked about this. And let me give you the exact version of Bayes' theorem. So the probability of H, if you've got H1, H2, H3 up to Hn, these are your hypotheses. P of H1 up to P of Hn priors. Are exclusive and exhaustive. So you know that exactly one of these hypotheses is correct, and you've got some opinions about it. So in this case, the hypotheses A, B, and C correspond to three suspects. You know it's one of them, but you don't know who. You've also got likelihoods equals the probability of D given HI, which is the probability of seeing the data given that the hypothesis is true, which is a powerful tool in your thinking, or it should be. So what does Bayes' theorem actually say under these circumstances? P of HI given D equals P of H I P of D given HI over a fiddle factor that makes the probabilities add up to 1. Bayes' theorem in its full form. Prior probability here. Can you guys stop, please? I can hear you and it's putting me off, all right? It really is putting me off. If you don't want to be here, that's fine. But if you want to talk, can you talk outside? Prior. So this is your opinions. This is your likelihoods. This here is a fiddle factor to make probabilities add up. Okay, and we've covered this in excruciating detail. It will be nice to see more Bayes' theorems in your portfolios. I don't see very many people using Bayesian analysis in their portfolios. That would be nice. I would like to see that. Show me that you've understood it. So what are our priors? A, B, and C. A, B, and C correspond to three suspects. Priors P of A, P of B, P and C, 0.6, 0.3, and 0.1. The data is fingerprints taken at the crime scene. A is guilty. He would leave matching prints with a probability of 90%. So straight away, we've got P of H1, P of H2, priors, P of H3. And what are the numbers? 60, 30, and 1. See, they add up to 1 like they should. Prior. We've got likelihoods. What was that? 90. 90, 50, 10. 0.9. 0.5 was it? And P of. Okay. So we just apply Bayes' theorem. Well, let's work out the problem. Let's work out P of H1, P of D given H1. 0.6 times 0.9, 0.054. P of H3 so person C is unlikely to be the perpetrator for two reasons. Firstly, because he's rarely there, or she is rarely there, and secondly, the fingerprint evidence would indicate it's one of B or C instead. But further observe that these guys don't necessarily add up to 1.
Sorry, can I just say I think the first two that you worked out there, it's actually 0.54 and 0.15.
Oh, it is 2, isn't it? What am I doing wrong here? 0.54, 0.15. Yeah, you're absolutely right. Would I have caught that mistake, do you think, in practice?
Mentally.
Maybe I'd have caught it. Maybe I'd have caught it. Okay. So we just write that, and I'm just going to call this A, B, and C. And just expanding the denominator means that the probability of A, given the data, is A over A plus B plus C, because the numerator with I equals 1 is this one here, and it's just the sum of the other two. Equals 54 over 54 plus 15 plus 1. (54) divided by 60. All right, just going through Bayes' theorem, just dead easy like that. The next one, P of B, given your data, is just B over A plus B plus C, 15 out of 60, and of course probability of C given D is just going to be 1/60th. That's it. So it asks us, what are the posterior probs of A, B and C being guilty? Copy, paste, It's not done it very well, has it? The cutting and pasting isn't very good. Right then, so let's just go to R. A becomes 0. Which way around is it? 6 times 0.9. B becomes 0. C becomes 0.1 times 0.1, and then we need A over A plus B plus C, which is that B. My calculations are not doing very well. It's 70, isn't it? Because I've got a 1 to carry, which I missed. Sorry about that. 70. Did you see how I caught that error? Did you see how I added up wrongly? And did you see how I checked it? I've got A and B and C. A plus B plus C should have been 60 by my calculations, and I got 70 here. So that was why that was wrong. Yeah. So A over B and C. There it is. There they are. Right click copy. Go to Word. Right click paste. Make it red, make it Courier New, and we're done. You don't need to say the probability that A of a posterior blah blah. You don't need to, look, that means you understand it, and that's good enough for me. So I said 1%, that's 1 over 70, isn't it? A witness states that the perpetrator wore Nike brand clothing, or is it Nike brand clothing? Suspect A wears Nike half the time. Let's go back here. A wears Nike half the time, B 1/5 of the time, probability 20%, and C all the time. You may make the assumption that choice of clothing brand is independent of criminal activity. Maybe not being suspected of it. So now we can take these likelihoods here. We can do it two ways, and people did this both ways in the exam. The first way that people did was to take, I've lost them. The first way people did it, which I thought was that, it's not the way I taught it, but it's a better way of doing it, I think. People took these as priors and then put data on them. But the way I taught people to do it, and the way that I think about it is to say that we've got likelihoods of that, and then we've got data d dash, which is that times the probability of wearing Nike clothing, and I've forgotten the numbers now, of course. Half, a fifth, and all. A half, 0.2 times 1. If this one was 0, that would mean he couldn't possibly do it. Intuitively, you'd say, well, it can't have been him because the suspect was wearing Nike and he never wears Nike. So if there's a 0 in there, it all kind of works out because the numerator would be 0. But we'll leave it like that.
That would give you the same answer, wouldn't it? Your same posteriors if you take your original priors and add this new information.
Yes,
to your
it's the same.
posteriors.
Mathematically, it's the same. That's why it's good, because you can carry on adding more data and updating your priors in an objective way. So let's work out A, B, and C now. That's going to be 0.6 times 0.9 times 0.5, 0.3 times 0.2 times 0.3 times 0.5 times 0.2. That's 0.1 times 0.1 times 1. All right, so we just multiply those throughout. So you don't need to reproduce the equation as such, you just need to understand how it works. That's all I'm really looking for. There's another test which I've just thought. It's obvious here that this plus this plus this is going to be equal to 1, isn't it? Because it's A over that plus B over that plus C over that, and A plus B over C over A plus B over C is 1. So you don't need to bother with the check because it's obvious from the structure. But it's as well to check numerically. Look, 87 plus 3 is about 90%, plus about 9 it's about 100. Right click copy. Got a word. What are your posteriors now? Right click paste and we're done. Make it red. Courier new. Done. Give an example from Bayes' theorem in your everyday life. Your example should have 2 or 3 hypotheses, one of which is known to be true, as in the question above, some prior probabilities for these, and some data which you can use to calculate posterior probabilities. NB, a couple of sentences, is fine. Let me think what I would say for my possibility. I would say I get home and sometimes I walk straight in through my door and sometimes it's locked. And I've told my kids that if they're at home alone they should lock the door. But sometimes they forget. And sometimes they get home and the mother's home, my wife's home as well, and so she will leave the door open. So my data, door locked. My hypothesis, H1, is that Leslie's home, and H2 is that she's out. So what's my likelihoods? P of D given H1. There's my data, the door's locked. What's the probability that it's locked if she's home? Well, sometimes the kids lock the door and she'll come in through the French windows instead and leave the door locked, but that's rare. If she's out, I'd say, sometimes they forget. If she's out, they're supposed to have, technically, I tell them, lock the door, because there's all sorts of who knows what. So let's say that's 0.95. See, they don't necessarily add up to 1 because they're likelihoods. Let's have a look at, we need some priors. Let's think about priors. She works late 2 days a week. Well, let's try that. She works late 2 days a week. So she'll be out 0.4. So they add up to 1, all right? So we've got P of H1 given D. equals P of H1, P of D given H1, over P of H1, P of D given H1, plus P of H2, P of H, note D given H2. $95 times 4, 0 down 2 to carry, 36 to 7, 38, isn't it? 0.38. Okay, I think I've got that right. So again, we need the probability of H1 given D equals 6 over 6 plus 38 over 44. So what does that mean? The probability that she's home, given that the door is locked, is this small probability. Because if she was home, she normally opens the door. But sometimes she walks in through the French doors. Okay? How do I get marks for that? I'll just write this and then I'll stop for 5 minutes. Okay, so we've got H1, wife home, prior P of H1 equals, what is it? 0.6. H2, wife not home, prior P of H2 equals 0.4. Exclusive if she's home. If she's not home, she's not home. And if she's not home, she's home. It's one of these. And I've covered all the bases. So these two can't, there's no overlap. We haven't got this kind of business here with an overlap. They're distinct. And there's nothing outside. She's either home or not. Data equals door locked. Likelihoods. P of D given H1. What did I say? 0.1. Oh no, I've got this the wrong way around, haven't I? Which way around is it?
Yeah, that was right. 0.1.
0.1. That's right, yeah. P of D given H2 equals 0.95, yeah? You don't have to do it in R, it's a bit silly. A becomes 0.6 times 0.1. B becomes 0.4 times 0.95. Oops. That's it. Copy. Paste. Make it red, make it Courier new, and we're done. Airbrush that out of existence. Done. There you go. Who thinks they could do that question in exam conditions? See, I'm not asking for anything super difficult here. This is perfectly reasonable. I'm not absolutely sure, but there may well be a question like this on the exam, yeah? You need to come armed with an example from your own life. And I don't want everyone to copy from each other because I can tell. It needs to be yours. Right, I'll stop there for 5 minutes.